And we're back. So we're about to start the final group of talks for today's portion of the 3-day conference. And our first speaker is Paul Roldorf Caster. Paul is a faculty member at the Computer Applications Department, and he graduated from the College of Computer Studies in the Mindando State University Iligan Institute of Technology. And Paul's talk is about a do-it-yourself weather monitoring station. So Paul, over to you.
Hello.
You
Am
had
I
me worried
audible?
for a minute, Paul.
Oh, I'm really sorry. I'm really sorry. So can you see my yeah, I, I
Well, you're coming
my
through
screen.
loud and clear.
Share my screen. Wait a minute. Wait, is this me? Yep. Can you see my presentation now?
Yep, that's great. Thank you.
Oh, okay. Thank you. Thank you. Okay. So I'm Paul Pastor, a faculty from the Computer Applications Department from the College of Computer Studies in the Mindanao State University Iligan Institute of Technology. And today I'm going to present to you my presentation entitled DIY Weather Monitoring Station, an example of a guide to beginners in firmware development. So now let's proceed. So as shown in the presentation is the process. So the steps consists of uh, 8 steps. So first is the requirement, technical specifications, hardware design, firmware architecture, firmware design, program flow, project setup, and testing phase. So every project should solve a problem, and that is meant for the requirement phase. And for the presentation today, I'm going to work with a weather monitoring station. And from the requirements, we will derive technical specifications, and from there we will derive our hardware design. Yes, we design the hardware first before the firmware, and for the hardware prototyping you can just do it yourself. And from there, from the hardware design, you can create a firmware architecture. And next is the firmware design, and yes, firmware architecture is different from the firmware design. And finally, we will create a program flow rather. Then we proceed to the project setup and the testing phase. So for the requirements, um, I would list the requirements that I set for the weather station project, and the rationale why I choose the weather station project, because it is simple enough and at the same time complex enough to show you the firmware development process. There are literally countless projects that I can use, but I think just one project is enough and fast enough for me to make my guide, since I also happen to have the materials lying within my small laboratory. And here are the requirements. So first is the system should be able to measure environment's temperature and humidity. Next one, it should be able to set, get real-time date time value. Next one is it should be able to display the current sensor data and time. And next one is it should be configurable interval for sensor measurement reading, and should be able to, the time zone should be configurable. At the same time, it should operate 24/7. And the last one is it should use ARM-based MCU. And notice that the requirements are silent about how we do things. The requirements dictate what features we need to fulfill. And the requirements can actually specify even more specific limit, such as technical specs like accuracy, humidity tolerance, at the same time say for example, error percentage and so on. And even for specific situation, you may also specify, say for example, the MCU that you are going to use. To say for example, your boss, say for example, requires you to use STM32 based, then you should go with the STM32 based microcontrollers. And for this one, we now proceed to then we'll now proceed to the technical specifications, and we can choose anything we like as long as the solution fulfill the requirements, unless explicitly written in the requirements. For example, just what I said is we need to use the CM32 microcontroller as suggested by the bosses or as required by the boss. And technical specifications can include programming language of choice and tool choice. So, say for example, if a team of four doesn't know Rust, then perhaps you don't need to use Rust. Unless it's a toy or experimental project, then don't use something completely new. So the technical specifications that we can derive from the requirements are the following. So for the temperature and humidity, we can use the simple module available, almost available perhaps everywhere. So we can use the DHT22 temperature humidity module. For the MCU, I specifically choose the RE603 since I have the development board that I happen to be to won last embedded UI competition hosted by Artifred last year. And the display is the 4.3 inches LCD 16-bit with 480 times 272 resolution with RGB 888 and capacitive touch um, features. Next one is for the daytime. We can use the RTC module such as BS3231. And for the storage is we can utilize internal flash using LittleFS and the USB power. So remember, this selection is directly limited to the requirements. And let's say the project needs humidity accuracy of positive negative 1% and temperature accuracy of positive negative zero point degrees Celsius, then we need to eliminate the THT22 and look for some better alternatives. And the process of choosing the best component within specs is called component selection for electronic product design. And the component selection for electronic design is a process where developer scour hundreds of pages of datasheets, application notes, reference, design, and manufacturer portfolio considering the technical, such as the functionality, DC electrical characteristics, AC electrical characteristics, power consumption, physical size, supporting circuit elements, operating environment requirements, and reliability data, as well as regulatory and compliance requirements, the IP or the intellectual property, development tools, and IAC platform, and scope for enhancement, as well as the non-technical parameters such as the cost, multiple sources, stage of production, and the legacy. And next one is from the technical specifications, then we need to derive or to create a hardware design. And please note that the from a firmware developer perspective, hardware design isn't the same as hardware schematics. And hardware design is the sense, in this sense, is the layout of physical parts that makes the system. The aim is to help the firmware developer understand what peripherals need to be initialized, what drivers to write, etc. Usually, to simplify things, we create block diagram to show the system, but hardware schematics will also do. Although it has many visual noise, passive components, crystals, analog circuits, resistors, capacitors, transistors. And in this project, we don't care how the HT22 circuit is designed. All we want to know is what protocol we are going to use and what GPIO pins and MC will use. The same goes with other parts. And here is the example of a hardware design for our weather monitoring project. So we have MCU RA6 integrated sender, this one, and we have the DHT22 connected to the RA6 M3 microcontroller through a GPIO pin. We also have DS3231 RTC module connected to the RA6M3 via I2C communication port, as well as the TLCD, which is commonly connected to microcontrollers with regards to I2C communication protocol or the SPI communication protocol. Then we have the serial terminal for debugging purposes and other purpose also, and we have the little FS. And for more clarity, we can add the text I2C or perhaps SPI or perhaps GPIO in the arrow to the and this seems simple, but extremely large project making this block diagram will insanely help firmware developer navigate the system complexity without diagram noises, and we help reducing mental effort to understand the system. And after making our hardware design, we are now ready to design our firmware architecture. And this is the firmware architecture that we can derive from the requirements. And firmware architecture is just a fancy term to describe how you model the internal parts of the firmware. You might call it a software stack. And for the weather station project is the firmware architecture is shown in the presentation. We have um, 5 parts, of which we have the business block up top in the box with reddish color, the weather station, which is called the top level class. We have the subsystem, the configurator, and the settings, as well as the interfaces, which is in pure abstract classes, as well as the drivers. So as you might have noticed, um, the in the violet box are all hardware independent, and in the yellow box down here are obviously hardware dependent. And designing firmware architecture first is a great practice because it forces firmware developers to think about system level design and not implementation levels. And kindly note that firmware architecture is different from the firmware design. Architecture is all about abstraction and layering, while the design is all about how we will actually implement those architecture or other the plan. And yes, we need to design the firmware architecture, but we also need to design the firmware design. So the orange box above are the interface, and interface is a contract between module, which are in green or blue in the figure, and driver, which are in yellow boxes. And next is we're going to our firmware design. So this I copied the requirement list here, as well as the updated requirement list. We can eliminate the last 3 points because it's not directly related to the firmware. The next part is the copy of the firmware architecture, and here is our firmware design. Now we need to specify the APIs or functions for each block in the diagram, and we can start from anywhere actually because design depends on each designer's practices. Some designers prefer to start from the requirements and then fill the rest. Also, some designers prefer to start from the driver all the way up. And at the same time, also, some designers prefer to start in a random way. And my point of view is as long as the final design is well defined and consistent, there's nothing to worry where to start. And for me, my approach to the firmware design is to start from the driver and then fill the requirements. And this is the flow I would take in creating my firmware design. First, I'll start with the sensor with the serial interface first. So in the serial interface, we'll have the function bool in it, the string read, as well as the bool write, which takes a parameter string s. Then second one is the sensor interface, which also has bool in it, and the float read temperature C, which is in temperature in degrees Celsius, as well as float read humidity. And for the temperature, you can specify whether you want it to be in a degree Celsius format or in Fahrenheit or in Kelvin, perhaps. Next one is the display interface. So as usual, we have the bool in it, the bool set temperature value, which takes a float parameter f, as well as the bool set humidity value with a float f parameter. Next one is the bool set datetime value with a parameter of string s. The next one is the time interface, which has a bool in it, bool set current time, which takes a parameter of unsigned 32, the next time, and the unsigned 32 get current time function. For the storage interface, we have five functions: the bool init, the bool write file, which takes a parameter of string file name and string data JSON. The third one is the string read file, which takes a string file name parameter, as well as the bool delete file, which has string file name parameter, and the bool exist string file name parameter. Next one is we will also design a firmware design with settings module, which has six functions: the bool load with string setting file parameter, the bool store, the bool set interval, uh, the get interval, the bool set time zone, and the get time zone. And now, because our time driver will store datetime in UTC plus zero, that means we need a helper class to show local time in a format of year, month, and then followed by date. And I'll probably, in my point of view, I will take this format. No, this format perhaps. So formatter string format time, unsigned 32 Unix time, and integer time zone. And the last thing is we need to define the JSON format for storing setting values. And this is the format that I came up with. So it has an update interval of 1000 seconds. 1 second rather, and the time zone of -7. And after everything with our firmware design, then we'll proceed to the program flow. So here's the design of our system. And this is the last part of the design section. Basically, you will dictate the device behavior via program flow. Program flow ideally should cover all general flow of the device and use flow diagram to communicate your thoughts. Program flow shouldn't too complex and too detailed because we want to know the data flow and how program behave normally. You might want to add another or perhaps a separate diagram to show negative flow where every step should handle every failure. And if we want to get the most detailed program flow, then we better off reading the source code directly. So here's the program flow. We'll have a start up here. Then next is the peripheral um, initializations. Then we need to load the settings.json, and we have a question here regarding update interval elapsed. If yes, then we'll proceed with the red sensor data update display. And if no, then we'll directly go to the process of incoming serial data. And if yes, then process the command, send response to the serial, and come back to the update interval elapsed. And now as we have designed all the important parts of the firmware, um, we need to do the project setup. So for the project setup, I chose, since I use the RA6M3 development board, I use the ArcThread Studio, and the ArcThread Studio is one-stop development tool. It has easy to use graphical configuration system and a wealth of software packages, components, resources, which makes IoT development simple and efficient. And in a timely manner, it so happened that all the requirements that I set for the weather monitoring station is covered or supported by the RT thread. So it makes the weather monitoring station easier. So in this part, you need to somehow first download the Articred Studio, and in by clicking this one, the free download button, and their Articred Studio website, the download section. And if you already downloaded the installer, I currently use Windows, and this is the installer of the Articred Studio. Then after this one, you need to install the installer. And after the installation process, then you can now create your own project using the Articred Studio. For beginners, here's the fresh look of the Articred Studio. If you are beginners, first time or first timer using the Articred Studio, if you open the program, this is what it looks like. And for the RA6M3 programming, here are the steps that are made. So first is you need to click the SDK manager indicated by the red box, this one. And then you need to install packages via the SDK manager of Articred. As you can see, I installed the version 5.0.2. It's up to you what version you want. As for me, I really wanted to use the updated one. And after that, clicking your desired version, then you need to click the install. And at the same time, we need also to install the support for the HMI board. So you can scroll down and in this DK manager, look for the Renesas tab or area. Then then you need to check the HMI board. At the same time, you need to install the. And also, you need to install the PyOCD for you to be able to use the Duckling so that you can upload your program to the HMI board. So you need to install the PyOCD version 0.2.1 as well as the Pi 0.2.0. And for the project setup, then you can now create your own project or a very simple project. Um, in my case, before doing all throughout the project, I usually test modules separately. So in this case, this is the steps I took in trying the lid blinking program, which is commonly equivalent to the Hello World in Embedded System program. So first, you need to click the file, new, and then the Articred Create project. The next one is you come up with this one, this create Articred project. You can create a project based on MCU or based on board. As for the HMI board, they are using based on board. So you can click based on board, and since you already installed the HMI board from the SDK manager, you can click the board HMI board. Then you can automatically choose between the template or the example. As for me, I choose the template with the Articred 5.0.1 and the adapter doubling in the port traceability or the serial wire debug. And after that, we need to build the project. You can click this hammer button up here below down the source in between the source and the navigate button. Next one is when we wait, and it should be able to build finished without errors or warnings. And after that, we're going to upload the program to the RA6M3 HMI board. First, you need to connect board to your laptop. Then at the same time, um, click the flash download indicated by the red box here. And after that, it should display that your code is uploaded successfully. And for the Articred, after you downloaded the template, you should be able to see that the built-in LED is blinking with an interval of half second. And the next one is the code implementation. For yeah, this is the code implementation part of our firmware development process, and this should be the most straightforward, if not the easiest part of the entire workflow. So in this phase, you just need to convert every firmware architecture and firmware design into concrete, tangible results. And we are aware that you might think that coding is hard, and it is hard if you only don't have a well-designed system. If you have a crystal clear clarity on what you should write and how you should do it, coding part should be easy. Um, that's why software system architects are paid far more than programmers or the design implementer. And and for our weather monitoring project, I implemented the code by converting the module interfaces into interfaces files and create the class for every module in the firmware architecture. And here's the steps I have taken. So first, I convert every orange box into interface headers. This means I have to create serial interface.h, display interface.h, sensor interface.h, and so on. Next one is I implemented the driver code in yellow boxes by using the interface above. I tested every driver code implementation to make sure my drivers are okay. Next one is I wrote the code skeleton for green boxes or the subsystems. And the next one is I create test cases for green boxes because they only have skeleton. They should fail the test. And I create the top level application weather station.h and weather station.cpp or .c. And finally, implement the business logic in main CPP or main.c. And for the RA 6 and 3, the main CPP, the main.c can be found in the RA gen main.c. This is generated and suggested not to mess with. However, if you are free, however, you are free to configure the SRC HAL entry.c for easy access for beginners. And the next part is the testing phase. So in the process of deploying firmware, we need to maintain the code quality and make sure code implemented is implemented as designed. And there is this is where we're going to the testing phase. There are a lot of testing, and here are the some of the testings that are commonly performed in the industry or as an embedded systems engineer. First is the unit testing. So you're going to test a single block of your module or module of your firmware. The next one is the integration testing. So this process tests multiple blocks to make sure they are playing nicely. Third one is the system testing. This is literally test the whole system to make sure it doesn't break. And stress testing, test how the system behaves under high load. And for the we also have performance testing, test how fast the system finish its work, such as signal processing project, object detection, etc. And the last part or the last testing is the power testing. For its purpose is to measure or to test how much energy the device eats while doing its job. For unit and integration testing, you can use the Catch2 framework if you want to do such testing. And the next part is the validation and the purification. So these are just additional steps if you are going to um, perhaps deploy or implement your system. So we need to have a validation and a verification part. So in this part, we have three. First is the compliance testing. So we need to ensure that the firmware complies with relevant standards and regulations, such as FCC/CE. Field testing. Conduct field tests to evaluate the system's performance in real-world conditions, as well as the user acceptance testing or the UAT. We need to get feedback from end users to ensure the system meets their expectations and performance. Next part is the documentation, which is a very important. Um, First is the technical documentation. You need to create detailed documentation for firmware, including code comments, user manuals, and maintenance guides. Next part is the release notes. Provide release notes that highlight new features, bug fixes, and known issues in the firmware release. Next part is the deployment, um, which is the firmware deployment and monitoring and maintenance. For the firmware deployment, deploy the firmware to production devices. This can involve methods like over the air or OTA updates for IoT devices. And for monitoring and maintenance, monitor the deployed firmware for issues and provide maintenance updates as necessary. And that's it. Thank you very much.
Well, thank you very much, Paul. Kathy's asked for anyone to give any questions. I did have a question. Are all the files and your slide deck available on a website somewhere? Because this struck me as being a very useful tutorial for junior embedded engineers, like all the testing and everything, the power testing, the compliance testing, having that as a tick list of things to do. So I wondered if you
Um,
had this as a package available.
Unfortunately, it's not available somewhere else. It's only available in my laptop. But if you want to have a copy, or yeah, a copy, you might want to contact me through my email. I'll be posting my email address here in the comment section.
That would be awesome. Yeah, so that people can contact you and yeah, no, that would be very handy indeed. So the DS3231 real-time clock, why did you pick that one? I use it myself all the time.
Actually, I've been using the RTC module like for how many years now? Because way back around 2015, 2016, IoT is not that common. So we need to somehow use RTC module in order for us to track time. So one of the things that I have currently laying around in my small laboratory is the DSP231. So I just grab it and use it for the project.
There are cheaper models, but that one is very, very accurate. I think it's plus or minus point 0.03. Sorry, 0.3 seconds a day. Yeah, which is phenomenally accurate, really, and very easy to use. So, yeah, as soon as you said that, I thought, oh yeah, I'm familiar with that. One of the other things that you talked about was the problem of component selection and having to go through hundreds of data sheets to find the best components for the task. And I wondered if you'd seen a tool called Flux.ai. Are you familiar with that at all?
Yes, I encountered and I happened to use it once, but unfortunately, its system requirements are too heavy for my laptop, so I stopped using it.
Okay, I'm posting the link here in case people want to do it, because that is pretty amazing. It's based on a large language generative AI model, and it's like GitHub Copilot for code. This has got its own Copilot. You can I've seen it do amazing things, like you can just say I want an 8-bit micro, I want a 32-bit micro, and I want this LCD display. What's the best way to connect them together? And it will go off and read the 300-page data sheets and come back and say you've got three options. You can either use I2C with 2 pins, but it's the slowest, or SPI with 4 pins and it's faster, or the very fastest is to use 10 pins, but that's 10 pins. And then it recommends one. And when you say, okay, let's go for this one, it'll wire it up for you and generate the schematics and everything. So very interesting. So thank you very much for that
Okay.
tour. That's great.
Thank you.
And again, I think there's a wealth of information there for people who are just starting out in embedded. A lot of people, it's like when you see all the projects on the web, there's a world of difference between creating a prototype that works, and creating a production model that that meets all the requirements, and having all those different testing and showing how you break everything out and separate the layers into the hardware abstraction layer and everything else. Very useful indeed. Okay.